Welcome to SanfordFlipMath. This is PreCalculus. We are working through the Demana, Foley, Kennedy PreCalculus book. And we are starting our new adventure in Trig, and that is Trig Identities. This is something that you've probably never done before. And this is probably what I would consider the most challenging part of the course. And much of that is really because you're going to have to remember a lot of what you're going to look at as formulas. Lots of equations, rules that you just plain have to know. All right, so this next unit we're going to stick with 5.1 through 5.4, which is all about trig identities. And identities are equations that are true for all values in whatever domain you're talking about. You already know some of these, like for instance, cosecant is equal to 1 over sine. That is a trig identity. It's a truism. It's like a conversion factor. It's like 12 inches equals 1 foot. It's true all the time. And it's just one of those little facts that you just know. So there are going to be a bunch of those that we're going to do. And what trig identities are used for is to simplify. So for instance, if you look at this guy right here, this is kind of an ugly little trig expression. It's disgusting looking. There's a lot of stuff going on. And a quick little note to self here, this notation sine squared x is written that way, and we say it that way, but really it means sine of x, the whole thing squared. We don't write sine of x squared, and because this is talking about the x being squared, not sine of x. Okay, and it gets even more confusing in the fact that your calculator thinks that what I just wrote actually is the same thing. Okay, so this can get a little troublesome. But anyway, back to my point. What we're trying to do is simplify expressions that look like this, and I'm just going to zip through this little example here just so you see what's going on. In just a couple minutes, we're going to talk about the fact that this sine squared plus cosine squared, based on the right triangle a squared plus b squared equals c squared, happens to be equal to 1. So since that's true, this is really 1 over cosecant x, and again I'll talk about why that is in a minute. And we know that cosecant is the reciprocal of sine, so the reciprocal of cosine, or cosecant, excuse me, takes us back to sine. So I would think that most of us would much rather look at this than this. Now the only catch is there's a little domain issue here that, cosecant doesn't have any values at, there are asymptotes at 0 and pi and 2 pi, etc., whereas sine has a domain that's all real numbers. And we could do some similar things with this one, and we'll see examples of that. Okay? All right, so trig identities are used to simplify trig expressions or to show that other trig identities are true, and that's really a 5.2 concept, but we'll be using that idea in a bit. Okay, substitutions are made in order to replace complicated expressions with simpler expressions, like sine squared plus cosine squared happens to be equal to 1. That's much simpler. Or sometimes we'll make some substitutions so that some things will start to cancel out. Okay, so as we go into these, you're going to see a long list of things starting to develop very, very quickly. And really what we're going to do today in this video is establish a bunch of rules, and I'm going to give you background, and I'm going to give you some ways to remember them, but that's the key, is you have to remember them. And when you get to college, there's no guarantee that they're going to let you use any kind of note cards or anything. So I need you to understand that we're going to need to know these now from your brain. So there's no note cards, there's no cute little list, etc. And there's a lot of these, and just know that it's going to be a lot. Okay. All right. Well, the good news is that some of these you already know or are very, very straightforward. Okay, so we're going to classify them, and I think that helps to remember them. The reciprocal identities are real straightforward, and as I said, you already know them. Since sine is opposite over hypotenuse and cosecant is hypotenuse over opposite, these are reciprocals of each other, and that's true for all of these. And likewise, the reciprocal of cosecant will get us back to sine, etc. So this set of 6 identities you already should know. Now, you already know from the unit circle that tangent is y over x. You also know that y is sine and x is cosine. All of this comes from the unit circle. So basically, by transitive property, we could take out that little middleman there and say that tangent is equal to sine over cosine. So this, because it's written as division, is called a quotient identity. Similarly, it's reciprocal. Now, you already know also that tangent's 1 over cotangent, and cotangent's 1 over tangent, but cotangent's also cosine over sine. Again, the reciprocal of tangent. Okay, so this is already, we already have 8 identities, but again, we haven't done anything that's really a new concept. Okay? All right, well, let me open up a can of worms. There's something called Pythagorean identities, and it is all shockingly, they are all shockingly enough based on Pythagorean theorem. So you already know that a squared plus b squared equals c squared. And I'm going to play around with this. Now this is something that we already know is true for any right triangle. And what we're going to do is divide both sides by c squared. And there's a reason I'm doing this, and again, this is background. And so I'm going to write this as a over c squared and b over c squared. And c squared over c squared is 1. Okay. Well, let me stick a little theta in here. Okay. And so that means that a over c squared, well, this is opposite, hypotenuse, and adjacent. So with that being said, a over c is really sine. And b over c is really adjacent over hypotenuse, or cosine. And as you recall what I just said a minute ago, we're going to use notation that looks like this, even though it really means what was previously written with the parentheses. It's just a shorthand notation. And this is the first and most important Pythagorean identity. This is very, very important, and so as far as new identities, this is the first one you need to memorize. This is the first one you need to know. Now there are some ways to rearrange this. Okay, so for instance, after we play around with this quite a bit, you're probably going to get very comfortable with the fact that if I subtract cosine squared from both sides, then sine squared will be equal to 1 minus cosine squared. Okay, now just like the Pythagorean theorem, let me remind you that this only works if you see those squareds in there. Okay. Similarly, instead of doing that, if I subtract sine squared from both sides, cosine squared equals 1 minus sine squared. Well, these are just different rearrangements of that same sine squared plus cosine squared equals 1. Now, I'm going to show you 2 more things you can do with this, and then I'm just going to give you a list. Okay, and you can play with it. Now, the heart of this, again, is sine squared plus cosine squared equals 1. Now watch this. I'm going to divide both sides by cosine squared. Now, again, I know that I can do this because I've done this 100 times. Okay, whereas for you, this is going to take some playing around with to remember how to do this. Okay, so sine squared over cosine squared is the same thing as sine over cosine, the whole thing squared, plus 1 equals 1 over cosine squared. So on the right side, this is secant squared, and on the left side, this is tangent squared. Well, this is another Pythagorean identity that we get from dividing both sides by cosine squared. Okay, similarly, there is one more that comes up, 1 plus cotangent squared equals cosecant squared. And again, subtractions of that. Now, this is moving really quickly, I understand. But what I'm trying to do is get you the background to get you to this. Okay, so this is the heart of the whole thing. You absolutely need to just know that one. Okay, and I'm going to try and do this throughout. You know, the reciprocal identities and the quotient identities you already either know or it's not a big stretch. This one is like, you know, not obvious at all. But once you know this one, then these are no big deal. And similarly, you can divide both sides by cosine to get this. And then these are direct results by subtracting from both sides. And similarly for this. Okay. Now, so just by knowing one identity, you can actually know 9. And again, what you're going to be doing is simplifying with these. So you need to know them well enough to work with them. Okay? All right, so these are less used. And this is a statement that I use to remember all of them. Okay, now here's the concept behind this. Pi over 2 is like 90 degrees. 90 minus an angle is the complement. Remember, angles that are complementary add up to 90. So here's the idea. Like sine of 30 degrees is 1/2. Guess what the cosine of 60 is? The let's do secant of 30 degrees is 2 squared of 2 over 2. Sorry, 2 squared of 3 over 3. And the cosecant of 60 degrees, the complement, is the same answer. All right, so the point being here, if you see a pi over 2 minus x in the middle of an equation, you can replace that expression with its co-function. Okay, so sine and cosine, secant and cosecant, tangent and cotangent, and similarly the other way around. So if it says cosecant of pi over 2 minus x or 90 minus x, cosecant, you can go to the secant. Okay, so again, if you remember this one idea that cofunctions are equal for complements, and cofunctions. I know I'm sounding kind of goofy, but saying it like that. But I need you to see that complements and the cofunctions go together. Okay. One more set of these, and these are symmetry identities, and these are like odd, even, and neither. So if you can remember that sine and tangent are odd, and remember that's kind of a graph issue as well, and if you remember some things about the shape of the graphs, then that can help you. And now the idea here is if you spin this 180 around the origin, then the graphs look identical. Okay, and for secant, it's symmetric across the y-axis, so it is an even function. So that being said, if you see a negative sign inside cosine, you can ignore it like it wasn't there. And similarly for its reciprocal. Okay, but for cosecant and sine and tangent and cotangent, if there's a negative on the inside, it's like there was a negative on the outside instead. Okay, this all goes to the f of negative x equals negative f of x. This is back from chapter 1. And this one is the f of negative x equals just plain f of x. All right, so what I'd like to do is let's pop back to the very beginning slide, and even farther back than that, the very beginning. There we go. Okay, and I just want to grab that initial expression, and we're going to take it and re-look at it. Okay. All right, so there it is. And again, what we're going to do is look for ways to make this look nicer. Okay, so what we did initially, well, let me just take you back. Now, this sine squared plus cosine squared, okay, that should look a little familiar now. It involves squared, so it's probably a Pythagorean identity, and it's at the heart of, it is the Pythagorean identity. It is the first one that we ever find. Sine squared plus cosine squared equals 1, and it doesn't matter. The key to this is, remember, what an identity is, it doesn't matter what the angle is. Okay, so like on this page it says x, and on that page it said theta. It really doesn't matter at all. Okay, all right, so sine squared plus cosine squared equals 1. Okay, so that means I'm going to make a replacement for it here and make it 1. Okay, and then the rest of this stays the same. Okay, and at this point, that is a reciprocal identity. We know that 1 over cosecant is the same thing as 1 over sine, or in other words, just sine. And I think most people would agree that this looks more simplified. And at this point, you know, you're just getting acquainted with these rules, so don't freak out yet. There's plenty of time for freaking out. Okay, now this one, the 1 plus sign and 1 minus sign, looks kind of like a rearrangement of that one. Okay, so let me just kind of remind you off to the side here. Sine squared plus cosine squared equals 1. So 1 plus sign, well, I know I can do a minus sine squared on both sides. So 1 minus sine squared, well, 1 minus sine squared is cosine squared. That looks a lot like this, but I need you to resist the temptation of doing that. It's not exactly that. It's similar, but it's not the same. This needs that squared there. Well, what you may not remember, but maybe you do, maybe you don't. If I had this thing, this 1 minus sine squared could be factored. Now, I'm actually going to go the other way. And let's look for a common denominator. To have a common denominator, it needs all of the factors of all of the denominators. So what I'm actually going to do is multiply on the right fraction by 1 plus sine squared. 1 plus sine. Also, it is a conjugate. We've done that kind of thing before. That's not why we're doing this. We're doing this because it happens to be the other denominator. And then on the first fraction, I'm going to do the same idea. I'm going to multiply by 1 minus sine. Okay, kind of out of room here, so I'm squeezing it in. Okay, so when I multiply these denominators now, on the bottom I have 1 minus sine, 1 plus sine, and so 1 times 1 is 1. I'm foiling, I'm distributing. Outer is going to be plus sine x. I don't usually write this. Inner will be minus sine x. For you, I'm writing this. Isn't that nice? That's what I call service. And then on the end, we're going to write minus sine squared because it's a negative times a positive. On the top, we got a bunch of distributing to do. So 1 minus sine times cosine, that's all of this stuff. This is going to be cosine minus sine x cosine x. I'm going to run out of room. Tell you what, I don't really need this anymore. So we'll just get rid of it. Okay. All right, so continuing on, we distributed the first numerator. I'm going to distribute the second, so plus cosine. And then plus cosine sine. I'm going to write this sine cosine just so they look the same. Okay, so a couple things to notice here. That goes away with that. They add up to 0. These add up to 0. On the top I have 2 cosine x. On the bottom I have 1 minus sine squared. That is what I said a minute ago was a rearrangement of sine squared plus cosine squared. Okay, so 1 minus sine squared, and again, you're going to get used to these. Okay, so here are those versions. So 1 minus cosine squared is sine squared. 1 minus sine squared is cosine squared. Okay, I'll stop on that page in a second. Okay, so this is now cosine squared on the bottom. I have 2 times cosine on the top. Okay, and so that means the bottom is really cosine times cosine. So one of those cosines divides out, leaving 2 over cosine. Now here comes the last little tricky step that is not obvious, but it's still going to happen. Okay, this is the same thing as 2 times 1 over cosine. So that means this is really 2 times secant. Okay, Alright, so I know we just did some scary stuff, but the point of this is to be able to take something that's ugly and make it into something that's a whole lot less ugly. Okay, sometimes in the path of science or engineering or whatever, you end up with some crazy convoluted ugly trig thing, and then the question is, can we make it look nicer? Well, sometimes you can, sometimes you can't. This is a situation in this case where we could. Okay, and this is what our focus is going to be on for all of section 5.1, and we'll have another video on 5.1 just about examples. But before I leave that, let me just end on this page. This is what I referred to as my abridged big list. Okay, now this is scary. Now, abridged means shortened, which I think is funny, and big list means big list. So this is kind of my way of trying to cut things down a little bit, but it's still a pretty big list. Okay, so just to kind of focus on some things here. You already know these, and then there are three others that are very much like them. This is a pretty easy concept because it's just y over x. Sine of theta over cosine of theta, again, all from the unit circle. This is the big daddy. This is the one that really, really needs to be memorized. You can divide this one by cosine and get that one. You could divide it by sine and get that one. So there are ways to get the other ones without memorizing them. And again, these are about symmetry of the graphs. The sine and tangent are odd functions, and cosine is an even function, if that helps you remember. And this is the one with all of the pi over 2 minus x's in it. Okay, because complements are about angles that add up to 90, and cofunctions like sine and cosine, secant and cosecant. Now, the other identities up here are going to be in section, this is actually section 5.3, and this is actually section 5.4, and yes, we're going to have to know them. So my advice to you is start with these now. Okay, again, you already kind of have those and kind of that, and then start memorizing the rest of them immediately. This is going to feel overwhelming. There is absolutely no way you can memorize all of these identities the night before the test. You need to, if you need to make flashcards or do something, I don't know what you need to do, but do something. Okay? All right. Thank you very much. We will come back at you with 5.1b next time. Bye-bye.